Hello and welcome to Module 2 on Drainage and Climate Resilience. Um, my name is Andrew Otto and I'll be taking you through this module. Now, the failure of low volume roads pavements can often be linked to poor drainage or drainage failure. Therefore, before embarking on pavement design, detailed consideration for drainage provision should be made. The contents of today's presentation are as follows. I'll go through the background and scope of the chapter. Then I'll look at external drainage, then internal and subsurface drainage, climate change in pavement design, climate change in design of drainage structures, enhancing resilience of existing pavements, and then I'll give a summary of key points that have been covered. Now, most low volume roads are constructed from natural, often unprocessed materials, which tend to be moisture sensitive. This places extra emphasis on drainage and moisture control for achieving satisfactory pavement life. Moisture is the single most important factor affecting the long-term performance of pavements. Thus, it is one of the most significant challenges faced by the designer, and the designer must provide a pavement structure in which the detrimental effects of moisture are mitigated to acceptable limits in relation to the traffic loading. The purpose of this chapter is to provide an overview of the key aspects of drainage and climate resilience that must be considered in order to provide a robust pavement that will be able to perform its function sustainably. The chapter does not cover detailed hydrology and drainage design. For those, you can look into your respective country manuals. Now, on this slide is a schematic representation of the contribution or the impact of the various aspects of environment as well as traffic on the long-term performance of low volume roads. We see from here that when the traffic levels are low, the damage on the pavement mostly occurs due to environmental factors. And as the traffic level rises, the contribution of the environment drops to a level almost about 40%, and the rest of it is contributed by traffic. Now, moving on to external drainage. The role of external drainage is to keep water away from the road. It therefore includes aspects or elements such as drainage ditches, culverts, surfacings, shoulders, and the road cross-section, and to some extent, the road alignment. Water can ingress into the pavement layers through, one, the surfacing. Over time, oxidative hardening of bituminous layers and cracking of the surface allow water to get into the lower pavement layers. For modular pavements, water can ingress through the joints between the modules, and for concrete through the cracks in the concrete. Now, when this water gets in, it weakens the top areas, which are also the high traffic stress zones, and therefore damage becomes rapid and easily manifested. The second way in which water can ingress into the pavement is through unsealed shoulders. Water easily penetrates and weakens material below the wheel pads, which are again the high stress zones of the pavement layer. Now, the third way in which water can ingress into the pavement is through low crown height. A low crown height may allow water running or ponding into the side drain to ingress into the pavement layers. The crown height is represented by the symbol h mean in this figure. And another important factor is the invert depth, represented by d mean in this figure. It is important that the invert depth exceeds at least 150 millimeters to minimize the risk of water in the drain wetting and thus weakening the pavement layers. The methods of water ingress into the pavement that we've discussed also apply to unsealed roads. The difference is that for unsealed roads, there's a wider surfacing which would allow more water to get in through the surfacing, and this can be counteracted by having an adequate crossfall or camber of 4 to 6%. Now, to illustrate this, I put together a couple of photographs here to show the effect of having either narrow strips of unsealed area at the shoulders or having unsealed shoulders. The photograph on the left shows a narrow strip of unsealed area between the carriageway and the side drain. As you can see, water has been entering into the pavement through this narrow strip, and it has begun weakening the pavement and leading to subsequent failure through cracking and potholing. On the right is the situation that you would or you should aim at. That is making sure that the seal edge meets the edge of the side drain so that water drains straight from the carriageway into the side drain. Now, how can we prevent water from entering the pavement structure? We can do this through timely maintenance of rejuvenation seals or through reseals so that the edge hardening and cracking does not occur on bituminous sealed roads. We can prevent ingress of moisture from the pavement edges by sealing the shoulders and by raising the embankment. We can also make use of impermeable seals such as Otto seals and Cape seals. And we have to ensure an adequate crown height and invert depth as described earlier. Now, in some cases where you're doing work in retrospect to preserve a pavement, you may have to use dense graded materials on the shoulders to make sure that the ingress of water is not does not affect the pavement. You do not want your road to look like this. This picture represents the damage which the combined effect of poor drainage and traffic action can impart upon your road. As you can see from this picture, the side drains are virtually covered with vegetation, and the roadside does not allow water to run off easily from the carriageway into the would-be side drain. And the resultant effect at the end of it all is excessive potholing, and the road becomes impassable. Now, we move on to internal and subsurface drainage. Internal drainage is concerned with the movement of water that enters the road pavement despite an efficient and functioning external drainage system. This can happen through infiltration from higher ground or capillary action from below the pavement, or if the side drains do not have adequate crown height or invert depth as earlier discussed, and also through the surfacing if it is cracked. Now, the diagram here shows a kind of construction that you should be very wary of. If you have a permeable base, as shown in figure 3, and you have an impermeable shoulder, as shown by figure 4, you must always make sure that the shoulder is sealed. We now move on to internal and subsurface drainage. Internal drainage is concerned with the movement of water that enters a road pavement despite an efficient and functioning external drainage system. This can occur through infiltration of water from higher ground surrounding the road pavement, or capillary action from below the pavement layers, side drains that do not have adequate crown height and invert depth, and through the surfacing, which may be cracked. The diagram here shows a kind of pavement construction that you need to be wary of, and that is if you have a relatively impermeable shoulder and a relatively permeable base, as illustrated by arrow 3, you need to ensure that your shoulders are sealed as illustrated by arrow 2. This is to prevent what is called the boxed-in construction that traps moisture or water into the lower pavement layers if water gets in through the surfacing or through an unsealed edge of the shoulder. Ideally, if you have to use this kind of construction, you must provide a drainage layer on the shoulder as illustrated by arrow 7. Now, the best approach to avoid the boxed-in type of pavement construction is to use road bases and sub-bases that extend right up to the edge of the side drain as illustrated in this figure. Note also that the shoulders are still sealed, as we often advise. Now, we have to look into aspects of improving internal drainage so that all the detrimental effects of moisture migration into the pavement layers can be minimized. Now, I have to describe here something known as permeability inversion. Permeability inversion occurs when the permeability of the pavement and subgrade layers decreases with depth. Under infiltration of rainwater, there is potential for moisture accumulation at the interface of the layers. The creation of such a patch water table often leads to rapid lateral wetting under the seal. This may lead to base or sub-base saturation in the outer wheel track and result in catastrophic failure. A permeability inversion will often occur at the interface between the sub-base and the subgrade because most subgrades are cohesive and relatively impermeable fine-grained materials. preventing permeability invasion can be achieved by ensuring that the permeability of the pavement and subgrade layers are at least equal or increasing with depth. For example, the permeability of the road base should be less than or equal to the permeability of the subbase in a three-layered system. However, for low-volume roads, there is seldom a wide range of choice of materials, and if permeability cannot be avoided, the road shoulder should be sealed to an appropriate width to ensure that lateral wetting does not occur under the wheel tracks. And therefore, the best approaches at improving internal drainage include avoiding the boxed-in type of construction by ensuring your road base and subbase layers extend to the side drain, using sealed shoulders, avoiding permeability inversion as I've discussed earlier, and where all other approaches cannot be applied, you should consider providing subsurface drainage system such as French drains, interceptor drains, filter drains, or drainage blankets, and of course assuring adequate ground height and invert depth. We shall now look at climate change in pavement design. Road engineers are accustomed to designing infrastructure for a specific type of climate, but the climate they're designing for is no longer fixed. The climate is changing, which means basic designs on historic patterns and averages is no longer sufficient. Information on the future climate needs to be taken into account. The exact type and magnitude of future changes will vary by geographic region and with the amount of global greenhouse gas emissions. Now, the climatic changes that are already occurring are precipitation, which is more likely to fall as more intense rainfall events. We are also witnessing changes in the timing of the wet and dry seasons. There is less precipitation in some areas and more in others. There is also sea level rise, and this will affect countries that have got several roads, including low volume roads that run close to coastlines. There are also areas which experience greater periods of drought. And then there are also higher average annual temperatures and higher maximum temperatures. There are more frequent and intense heat waves in other parts of the world. Now, how can we integrate climate change into road design? We can do this through early assessment of climatic change in the design process. This means we should engage engineers, climate scientists, geologists, hydrologists, and stakeholders at the planning stages before we undertake our projects. We should also design for future flexibility, for example, by leaving extra space for future drainage structures. We can also improve our rehabilitation designs. For example, certain sections of road or structures that fail can be replaced with more resilient ones during rehabilitation of the various roads. We can also include adaptation measures as part of routine maintenance. For example, every year you could replace some culverts on your roads with much bigger ones or with others that are more securely anchored. We can also select more robust materials for sections at risk. For example, we can use crushed rock as road base in sections that are likely to flood and thus cause weakening of the road base materials if the natural materials with high plasticity were to be used. We can also review our design standards. For example, the crossfall and camber of our roads can be revised from 3% to 4% as a minimum. We can also review our material specifications and learn from the roads that would have survived extreme events. We can incorporate climate change into road design at the procurement stage. That is, a tenderer who shows experience of designing climate resilient options can be given extra points. We can also change designs, for example, by encapsulating vulnerable road sections with stone pitching or with concrete. We now move into climate change in design of drainage structures. Integrating climate change into design of drainage structures can be carried out through increasing the width of drains, e.g. from a minimum of 500 millimeters to 1,000 millimeters. We can also reduce the spacing of drainage structures such as mitre or turnout drains to divert water away from the roads. But bear in mind that in many countries, you'll face a lot of opposition if you try to create mitre drains that turn out into people's farms or into people's compounds. We can also use an appropriate storm or flood return periods for high-risk areas. And for example, we can use a 50-year return period for areas or structures where we have been using a 25-year return period. Now, I must point out here that the storm return period does not mean that the storm will take, for example, for a 50-year return period, does not mean that it will take 50 years for the storm to occur. You can experience a 50-year return storm almost twice in say 10 years, as countries like Mozambique have seen recently within the last 10 years received massive cyclones. So a storm return period simply means the probability of the storm occurring in terms of years. Now, we can also integrate climate change into drainage structures by the use of monolithic structures. Monolithic or composite structures consist of a single unit rather than discrete structural units. Monolithic structures include box culverts, causeways, and others. Non-monolithic structures include bridges and culverts with discrete elements. For example, a bridge normally consists of structural elements such as abutments, piers, and decks. These are not connected. They provide support discretely, but it is relatively easy for each element to be washed away or displaced. E.g., the bridge deck can be lifted or the pier can be washed away. These failures do not require much force to occur, but for monolithic structures, much greater force is required for their failure to happen or for them to be washed away. As you can see in this picture here, there is a large box culvert with 4 openings, and the whole culvert is monolithic. So if this were to be washed away, it would largely stay intact and only be moved a few meters away and can be restored easily during maintenance. And this is one approach which you can take, that you wait for something to happen before you carry out the corrective action. Another example of a 2-outlet monolithic structure or box culvert is shown here. Once again, you can see that the probability of this structure being washed away is quite low, and if it were washed away, it would move only a few meters away and can be easily restored. We now look at enhancing climate resilience of existing pavements. In some cases where your pavement design may be upgrading an existing road into one of a higher standard, you may already witness certain effects of the climate change on your road sections or on some of your drainage structures. Now, you need to carry out a vulnerability risk assessment of the infrastructure before you embark on any actions. And you do this by evaluating the condition of the infrastructure. For example, for drainage structures, you can see whether wing walls are being damaged or erosions are occurring at the toes of various structures. For road sections, you can see whether the edges of the pavement are being eaten away or washed away. And the second assessment that you need to carry out is that of the road environment, to evaluate which sections are at risk of, for example, overtopping. Now, you may need to consult topographic, climatic, and soil maps to be able to tell which areas are at high risk or which sections or structures are at high risk. A key aspect in this assessment involves the assessment of land use. Changes in land use may lead to deforestation, which leads to increased runoff and increase in the quantity of debris in flood waters, which may lead to clogging of drainage structures. And once the drainage structures are clogged, you expect that the water then starts affecting the pavement structure as well. Another approach is to carry out monitoring of existing infrastructure. You may, with modern technology, you may actually be able to capture footage of infrastructure as and when they fail. And assessing the mode in which the failure occurs helps you to determine the most appropriate interventions required to improve the resilience of other similar road infrastructure. Now, you may also need to carry out forecasting for climate change. Thankfully, these days, the models for forecasting are becoming more easily available. And under the RECAP program, some forecast maps for parts of Africa have been produced. You can get this off from the RECAP website. Now, you may also need to take very careful records of the condition of the existing infrastructure and data related to storm intensities, because the severity of the storm will most probably be manifested in terms of its intensity. And knowing the intensity allows you to design drainage structures adequately. In most cases, we get records from weather stations that simply report the monthly rainfall if you're lucky, and in some cases, or most cases, the annual rainfall, but the intensity is often missing, and that is what you need for design purposes. Now, in summary, we can see that to ensure good drainage and climate resilience and longevity of road infrastructure, you must consider sealing shoulders for any pavements that you provide, providing adequate crown height and invert depth for your pavement that you will design. You should carry out or program the resealing of roads in a timely manner. You should consider the use of subsurface drains or drainage layers when internal drainage is at risk and no cheaper options can be provided. You need to address or attend to road sections that may be at risk of climate change effects. You should also consider increasing standards such as crossfall camber, the size and the frequency of your drainage structures, and consider the use of monolithic drainage structures. You should note that handbooks covering several topics such as climate vulnerability assessment and climate adaptation have been produced under the RECAP program and can be downloaded from the RECAP website shown on this slide. Thank you all for your attention.